So in my last video, I looked at the midpoint rule, which is a Riemann sum. If you haven't seen that, I'll link it in a card on this video. And a Riemann sum is just basically a finite sum which approximates an integral. And this video is going to look at the trapezium rule, which is a different Riemann sum. It's another Riemann sum. So to start, another method of numerical approximation of an integral. So to start, let's just consider a generic function. And again, I'll call it f of x. So it looks like this. It's just as generic as the last one. And we want a definite integral. So we want an integral from some value of a to some value b. And let's get a ruler up here. So we want the area under this graph from A to B. Now to do that, let's divide the x-axis into a bunch of values. Evenly split the x-axis like that. That's okay. And this distance here we're going to call h. So that's h, and this is also h, and this is also h, and you get the picture. And I know I've only drawn it, so there's 5 widths here, but there are n widths, right? So similar to the last video, this distance here is just n times h, because there's n widths, right? It looks like there's 5, but there's a skip a few somewhere there. So let's bring this up to the function there, and we'll bring this one up there, just like this. And then let's make some trapezia from this by doing this. So you can see there that I'm making these trapezia. And we want to find the area of these trapezia and then add them all together. Now, this is why it's an approximation, because there's this space that you're missing out there. There's space that you're missing out there. There's space that you're overcompensating for there. There is space here that you're overcompensating for, and here as well. And we'll discuss that a little bit later, but that's fun. But that's why it's an approximation. So again, the more trapezia you have, the better the approximation will be. So, okay, let's call the y-coordinate of, and these are the points at which the trapezia meet the function f of x. So let's call these points, call this one y0, y1 for this one, and these are the y-coordinates of those points, just the y-coordinates. Let's call this one y2, this one can be y3, then we're going to miss a few, then you've got y of n minus 1, and then y of n. So you can see there are n y-coordinates, well there's n plus 1, because you've got this y0 here, but these are all the y-coordinates of those points. So we can see that the height of this, that is to say this length here, is just y of 0, right? And this length here is just y1, and this length here, well, that's just yn, right? So that gives us the height of these trapezia. So let's call the area of the first trapezium A1, and this one can be A2, this one can be A3, then we're going to miss a few, this can be A of n minus 1, and this can be A of n. These are the areas. So similar to the last one, the integral from a to b of the function of x with respect to x is going to be approximated, and it's approximated because it's an approximate value because of these red spaces that we're missing, is just going to be a1 plus a2 plus a3 plus, you get the picture by this point, plus a of n minus 1 plus a n. Okay, well, what's a? What's a of n? What's the area? Well, recall that the area of a trapezium is just the average of the two parallel sides times the width of the trapezium. So in this case, it's going to be the average. So let's consider A1. It's going to be this length times this length over 2. So it's the average of those two lengths times this width here, right? That's going to be the area of the trapezium. And you can look that up if you want. I'm not going to prove it, but the area of a trapezium is just the average of the two parallel sides times the width. So that is going to be, well, A1, you can see it's the distance y0 and the distance y1 at the two parallel sides. So that's just going to be y0 plus y1 over 2 times the height times the width, right? And then A2 is just going to be y1 plus y2, because you can see the area of this trapezium is just this length here, plus this length here over 2, the average of those two lengths, times this width here, right? And that continues on over 2 times the height, and then similarly we're going to get y2 plus y3 over 2 times the height, plus all the ones in the middle, plus y of n minus 2 plus y of n minus 1 over 2 times the height, plus y of n minus 1 plus y of n over 2 times the height. So that's the sum of our areas. We can simplify this. We can factorize out the h plus 2. H over 2, sorry. So it's h over 2, and then you've got y0 plus y1 plus another y1 plus y2 plus another y2 plus y3 plus, what's that? Well, all the ones in the middle, plus y of n minus 2 plus y of n minus 1 plus another y of n minus 1 plus, at the end there, y of n. Okay? Hope you agree that that's the same. And that, well, you can see that that is just h over 2, and we've got one lot of y of 0, but we've got two lots of y of 1, and we've got two lots of y of 2, and although you can't see it, we have two lots of y of 3, and all the way up, and we have two lots of y of n minus 2, and we have two lots of y of n minus 1, but we only have one lot of y of n. And so that is commonly written as h over 2 times y0, again factorizing out the 2, y3 plus all the ones in the middle, and I missed out y of n minus 2, but it's included in there. Close the bracket plus y of n, close the other bracket, and that's the trapezium rule. This bit right here. Okay, well, what's h, I hear you say? Well, let's figure that out. We know that this distance is n times h, so this distance nh is just going to be b minus a, right? Because the distance here, that's the origin, b minus a is that distance. So nh is b minus a, so h we can see is b minus a over n. Right. Okay, so that's the trapezium rule, where h is b minus a over n. And similarly to the last one, y of I, let's say y of I is the set, let's do that better, it's the set of y0, y1, not plus, y2, y3, all the way to y of n minus 1 and y of n. So that's what y of I is. Y I is a set. And we can see that f of xi is just yi. So it's just saying that if you take your x coordinate and you plug it into the function f of x, you'll get your y coordinate. And xi, in the same way as in the last video, we can see that, okay, well, x1 is just this coordinate here. That's x1, pen battery low. That's going to be x2, that's x3, right? And so on. So we can see that x1 is just a plus h over b minus a. Okay, so it's just an nth of b minus a. So x1 is going to be a plus h, just h, right? A plus 1h, okay. Well, x2 is going to be a plus 2h, right? Because we've got x2 is just going to be a plus that h plus that h plus that h is going to give us the x coordinate there. And that continues. We can see that, we can see that x3 is a plus 3h, so we can see that xi is just a plus I times h, where of course h is b minus a over n. So you can also see the trapezium rule, this, written in terms of x. So you might see it as f of x0 plus instead of y0, but it's functionally the same. And yeah, that's the trapezium rule. I hope that all makes sense. Let me know, because you can actually compute, you can get a computer to do this sum right here. Pretty simple Python script to do that for you, and it'll give you a far better approximations, because you can have millions of terms instead of having to do it by hand. But that's the basics of the trapezium rule. Now let's talk about the concavity. Okay, so I'm going to do this down here. So if you have a concave, so okay, this is an approximation, right? We've established that the trapezium rule is an approximation because of this red area, this red space that it fails to account for, or it overcompensates for. So, well, how do we know if it's an underestimate or an overestimate? Well, that's to do with its concavity. So to show that, I'm just going to give you this. That is a concave down function, right? It's a concave down function. And we can see, if we divide it into some trapezia, we can see that if we have a trapezium like this, and we join it up, we can see that there's area underneath the curve of this concave down function that the trapezia don't account for. So there's that area that we're missing out, that area that we're missing out, that area that we're missing out, and that area that we're missing out. So when we add these areas together, the area of these trapezia, we don't account for this area between the top of the trapezia and below the function. So that means that that suggests that for concave down, it's going to be an underestimate, because there's space, there's area below the curve that we're failing to account for. Okay, then the opposite is true for concave up functions, like that. Let's do that again, like that. If we split the axes into a bunch of trapezia, we can see that there's area there. It's not so clear with those, but with that one you can see it. And there, you see, there's area that the trapezia includes that's not below the curve of f of x, below the function. In fact, it's above the function. Area there and area there, right? Perhaps I can make this a bit more obvious by doing it like this. Now you can really see that this is concave up, so there's area here that we're including in the approximation, but that's not actually under the curve of f of x of the function, it's above the curve. So that suggests that for concave up functions, concave up, it's going to be an overestimate. How do you check the concavity? Well, you just check the second derivative. If the second derivative is less than 0, then that's to say the rate of change of the gradient. If it's less than 0, then it's going to be concave down and it's an underestimate. And if it's greater than 0, then it's going to be concave up and it's an overestimate. So that's why with the trapezium rule we can actually identify whether it's an overestimate or an underestimate. And you can see back to our original generic function, on part of it there's actually a turning point in green. There's a turning point about there. So this bit's going to be this bit here. That bit there, that's not very well done. But this area here, that's going to be an underestimate. But over here, it's going to be an overestimate. Because this is concave up, this section is concave up, this section's concave down. So that's how concavity helps you see whether you've got an underestimate or an overestimate. But there you go. I hope you enjoyed the video. Thanks for watching. I hope it makes sense. Again, let me know if you want to see a Python script that will give you values for this sum here. It's really interesting actually, and it's really simple. And let me know if there's other methods of approximation you want to see or anything else. Thanks for watching. Don't forget to like and subscribe. And see you in the next one. Thanks.